Welcome to lesson 7.2, sampling distributions of a sample proportion. Your goal is to anticipate the shape, center, and spread of the distribution of p hat without having to do a simulation. Okay, so imagine a very large candy machine filled with orange, brown, and yellow candies. Think Reese's Pieces. When you insert money into the machine dispenses a sample of candies. In the activity, you will use an applet to investigate the sample by sample variability in the proportion of orange candies dispensed by the machine. So launch this Reese's Pieces applet on your own and try these things out. Change the population proportion of orange candies to 0.45. So one thing is that we have the population of candies. It's all the candies in the machine. The sample that comes out, and it's shifting it, the orange ones to the left and all the yellow and brown ones to the right. And then it tells you your p hat, your sample proportion of orange, even though the population is 0.45. This time the sample proportion was 0.52 when we just had 25 candies that we chose. Okay, and then we put a dot down here at 0.52. Okay, now if we took many, many, many samples, then we would build the approximate sampling distribution. Okay, so click on Draw Samples. An animated simple random sample of 25 candies should be dispensed. So this is the sample. The figure here shows the results of one such sample. Was your sample proportion of orange candies close to the actual proportion of 0.45? Look at the value of p hat in the applet window. Okay. Click Draw Samples 9 more times so that you have a total of 10 sample results. Click the Summary Stats and look at the dot plot of your p hat values. What is the mean of your 10 sample proportions and what is their standard deviation? To take many more samples quickly, enter 390 in the number of samples box and unclick Animate. And then click Draw Samples. You now have taken a total of 400 samples of 25 candies from the machine. Describe the shape, center, and spread of the approximate sampling distribution of p hat. So the shape is approximately mound-shaped and symmetric. The center is at 0.45 and the spread is at 0.09. How would the sampling distribution of the sample proportion p hat change if the machine dispensed 50 candies each time instead of 25? Reset the applet, take 400 samples of 50 candies, and describe the shape, center, and spread of the approximate sampling distribution. The shape is approximately mound-shaped and symmetric. The center is at 0.45 and the spread this time is a little bit less at 0.07. Okay, so what's the change? Less spread. As we increase sample size, we decrease the standard deviation. Now, set the p to a 0.05 and n equals 10, 15, 20, 25. Keep increasing n, drawing 400 samples. For what combinations of n when p is 0.05 is the sampling distribution of p hat approximately normally distributed? So we'd have to keep increasing from n equals 15 to 20 to 25 to 30, 35, and so on until we think that our mound is approximately normally distributed. Okay, just meaning that it looks kind of like our old tracings of our normal curves. And this is what my students in the class this day said. They said around 85 for the sample size, that they thought it looked pretty normal, 40, 100, 35, and so on. That these were each of their guesses for when they felt like the mound started to look pretty normal. Okay, so let's start getting some rules here. In the context of the candy machine applet, explain the difference between the distribution of the population and the distribution of a sample and the sampling distribution for the sample proportion. What are the individuals in each distribution? So this distribution of the population, it's the full candy machine. That's how we would describe it. And the individuals are the Reese's Pieces in the candy machine. The distribution of a sample, it's the bins below the machine. And the individuals are still the Reese's Candy Pieces. And then the sampling distribution for the sample proportion is the dot plot. But the individuals here are each of the dots, and each dot represents a sample proportion. So they are proportions, they are sample proportions. Okay? All right. Based on the candy machine applet and the penny activity, which I'm not going to go over here in the notes packet video, but describe what we know about the shape, center, and spread of the sampling distribution of a sample proportion. The shape is sometimes approximately normally distributed, but it depends on the sample size and the population proportion, P. The center is the mean of the dot plot. This mean, mu p hat, is approximately the same as p because p hat is an unbiased estimator of p. So the mean of the sampling distribution, we discovered a lot, seemed to be equal to the true the true proportion of orange M&Ms or orange Reese's Pieces in the candy machine. Okay, spread. Granted, we hold p the same for all the samples. Sigma p hat gets smaller as n gets larger. So sigma p hat depends on n and p. When is it okay to say that a distribution of p hat is approximately normal? So now let's get the rule. This is called your large counts condition. When np is greater than or equal to 10 and n1 minus p is greater than or equal to 10. So realize that there are two big extremes here. When p equals 0, so there's no proportion of successes. When p equals 1.0, and then everything in between, okay? So now if p is very extreme, like 0.99 or 0.01, then we would have to have a very large sample size. So 0.01 for a sample proportion times sample size of 15, it does not get us a value of 10. Okay, so 0.01 times 1,000 does though. So if you have a really extremely low or extremely high sample proportion, then one of these is going to fail unless your sample size is really, really large. And that has to do with the fact that as we increase our sample size, we decrease our standard deviation. And so if we are going to have a center right here, very, very close to 0.00, which there's no values less than that, then we would have to have a very, very, very narrow normal curve so that we have to have a really, really high sample size to have a really, really small standard deviation so that we can fit the whole normal curve between the center 0.01 and this wall 0.00. Okay? Same thing happens on the other side. Because we can't have any sample proportions more extreme than 1 or less than 0.0 or greater than 1.0. Okay, all right, so that has to do with that. Okay, look at small n and small p. Okay, so what are the mean and standard deviation of the sampling distributions of a sample proportion? So look what we're building here. We're first talking about the condition to assume that a distribution is approximately normally distributed. Now I'm talking about mean and standard deviation. Seems like I'm going right into normal calculations. So what are the mean and standard deviation of the sampling distribution of a sample proportion? Mu p hat is equal to the true proportion of the population parameter, and sigma p hat is equal to p1 minus p all over n. We can only calculate sigma when the standard deviation of the sampling distribution of p hat when the independence condition is met. So either we determine that by one of two things, by context. We have to explain that the results of one sample don't affect the results of the second. The results of every individual chosen in your sample don't affect sequential chosen people in your sample. And that the sample size, or if we're sampling without replacement, that the sample size is less than 1/10 of big N. That we're not sampling, if sampling without replacement from a finite population, we have to sample less than 10% of the population. Okay, these formulas are on the formula sheet. Are there conditions that need to be met for these formulas to work? Independence needs to be met and large counts, or normal large counts. So independence happens from the context or from less than 10% if you're sampling without replacement from a finite population. And the normal large counts is met if you can meet both of these, okay? All right. or if the population is, no, never mind. Okay, unless asked for, you don't need to check these conditions until we are officially doing inference in chapters 8 through 12, but you should still think about them and make sure that they are reasonable for each question. Okay, the superintendent of a large school district wants to know what proportion of middle school students in her district are planning to attend a 4-year college or university. Suppose that 80% of all middle school students in her district are planning to attend a 4-year college or university. What is the probability that an SRS of size 125 will give this one-time sample proportion of at most 75 students? So now we can find likelihoods of sample proportions. Our sample size is 125. And the true proportion is 0.8. The question is, what is the probability of getting a sample proportion, p hat, of less than or equal to 0.75? Okay, so independence, because we are sampling without replacement from a finite population, check that we are sampling less than 10% of the population. Assume that this large school district has more than 1,250 students. Okay, so great. Normal or large counts. NP is greater than or equal to 10 and N1 minus P is greater than or equal to 10. So N times P is 100 and N times 1 minus P is 25. Good, so we passed the normal check. So assume the sampling distribution of P hat is approximately normally distributed. Okay, remember that that's a sampling distribution of P hat. We're not just assuming that the true population proportion is normally distributed because it's just a distribution of yeses and nos. Okay, it's just 2 bars. Anyway, so calculations. The probability that P hat, a sample proportion, is less than or equal to 0.75 is the probability that Z is less than or equal to the Z-score for 0.75, the Z-score of negative 1.398, and then we get 0.082. About 8.2% of the time, after many SRSs of 125 students, 75% or fewer of the students will reply that they plan on attending a 4-year university when truly 80% plan on that. How do you answer a 4-step process? State what the problem is asking in the context. Plan, pronounce your inference method. We will use a 1 proportion normal calculations. Then check your conditions. Do all calculations showing work and marking answers clearly. And conclude, declare your recommendation or probability clearly. Suppose 90% of a school of size 2,000 students does their homework each night. Suppose you take a sample of 200 students. Describe the shape, center, and spread of this distribution. Shape, check the large count condition. Is NP and N1 minus P both greater than or equal to 10? 180 and 20 are both greater than or equal to 10, so the sampling distribution is approximately normal. Okay, so the center is mu p hat, which is p, which is 0.90, and the spread is sigma p hat, which is the square root of p 1 minus p over n. That's 0.9 times 0.1 over 200, which is 0.02. And the spread is possible because we check this condition, n is less than or equal to 1/10 of big N. 10 times 200 is 2,000. 2,000 is less than or equal to 2,000. So independence is met. Suppose instead someone takes a sample of 50 students. Compare the shape, center, and spread of this sampling distribution to the sampling distribution of 200. So the large counts is not met, so we don't know the shape. The center is 0.90 still, because it did not depend on sample size. And the spread is 0.04, it's double. So when I took the sample size and I divided it by 4, I only took the spread and divided it by 2 because of the square rooting. I took something and divided it by, I took a sample size and divided it by 4, but under the square root, 4 square rooted is 2. So the spread is times by 2. Okay, sorry, because the sample size is in the denominator, it does the opposite effect. Okay, and we would check to see that independence is achieved, and because we're sampling less, then yes, it's even further less than 2,000. Okay, in general, when you take a quarter of the sample size, what happens to the standard deviation? It is halved. It is doubled. And in general, when you take 4 times the sample size, what happens to the standard deviation? It is halved. Okay, thanks for watching.